Hello everyone and welcome to this introduction on limits. I'm going to be covering some basic definitions and a bit more of an advanced definition called the Epsilon-Delta definition. Now, limits are very vital to almost all of calculus. We denote a limit as lim of a function of x or any other variable. Then we have our variable down here, and we have an arrow which means it approaches some number, and we can call this a. And then this will equal some value b. So let's say under here on this graph of f of x equals x squared. So we have the limit of x squared as x approaches, let's say this point right here, which is at x equals 2. Now basically what this is saying is if we travel from the right on the curve and approach x equals 2, what is our y value approaching? So as we come from the right on this curve to 2, we get to y equals 4. Now if we go from the left side as well, as we get closer and closer to 2, we get closer and closer to 4 on the y-axis. But we're never actually considering the 0.24 itself. We're just getting infinitely close, but never actually getting there. So we can say the limit as x approaches 2 of x squared is 4, because the closer we get to 2 on the x-axis, the closer we get to 4 on the y-axis. Now this corresponds to with 2 squared equaling 4. So in this case, the limit as x approaches 2 of f of x is just equal to f of 2. Now this seems kind of useless then, like what's the point of approaching something if we can just plug it into the function and get our output? But if we have a discontinuity in our curve, then that's where limits start to come in more to play. Alright, so let's look at a different curve here. Now at x equals 2, we have a removable discontinuity. So let's evaluate f of x at this point, at 2. So f of 2 will equal 1 down here, since we have a empty circle here at 2, and then a filled-in circle at y equals 1. So the actual value is 1, even though it looks like it would be 2. Okay, now let's look at the limit as x approaches 2, not x at 2, of f of x. So if we come from the right here on f of x, as we get infinitely close to x equals 2, we approach y equals 2, even though that's not the actual value at 2. And if we do from the left side, as we get closer and closer to 2 on the x-axis, then we get to 2 on the y-axis. So since this limit from this side and this side are equal, then this limit does exist, and we say it equals 2 because that's what it's approaching. Now the right-sided limit here and the left-sided limit here have their own notation as well. And we denote it as limit as x approaches our value. And then in where we would usually have an exponent, we put either a plus or negative sign to denote which direction we're coming from. So a plus sign here means we're coming from the right side and going left. If we had a negative sign right here, then it means we're coming from the left to the right. So either way, from the right or the left, this is 2. So we can write this. We can also do this with a table of values. So if we start, say, with x, and then create f of x on this side, we can start at x equals 3, and then progressively get closer and closer to 2, but never actually touching it. Now we can do this on the opposite side as well. So I can do 1.999, 1.99, etc. Now in f of x, we just evaluate what the corresponding y value is for these x values. So let me write that in. Okay, so now that we have this table of values, I can also just plug in the actual x value of 2, which is equal to 1, again because of this point. But if we look here, we're coming from a greater x value down to 2, so this side would be the right-sided limit, because we're coming from the right of the x-axis to the left. So we can write this. And then from this direction, we're coming from a lower x value to a higher one at 2, so we're going from left to right. So then this is the limit as x approaches 2 from the left with a minus sign of f of x. Now if you look at here on f of x, as we get closer and closer to 2 from x, we get closer and closer to 2 in f of x, but we're never actually getting to 2. So we can say the limit as x approaches 2 from the right side of f of x is equal to 2. If we look at the left side, then we're also infinitely approaching 2 but never actually reaching it. So our limit there is also 2. Now finally, if we say this right-sided limit here is equal to this left-sided limit here, so the limit as x approaches 2 from the right of f of x, if that's equal to the limit as x approaches 2 but from the left of f of x, then that implies the limit as x approaches 2 of f of x exists, and it's equal to the right and left-sided limit. Alright, now let's look at this third example. This one's a bit more tricky. So let's try and find the limit as x approaches 2 of f of x. So again, first I'm going to do the right-sided limit. So I'm going to come from the right and then go to the left. So as we follow this curve from the right to the left, as we get closer and closer to 2, right here we're approaching 4. So I can say the limit as x approaches 2 from the right side of f of x is equal to 4. Now let's approach the same curve but from the left side. So as we go up this curve and get closer to 2, we stop and approach at y equals 3. So we can write the limit as x approaches 2 from the left of f of x is equal to 3. Now, so what does that mean? Is the limit as x approaches 2 of f of x 4, or is it 3? Well, since the right-sided limit and the left-sided limit are not equal, then that implies that the general limit as x approaches 2 does not exist. Now again, f of 2 does exist. It's 4 because of this dot here. But since as we approach from the right and from the left, we get closer and closer to 2 different y values, that means that our general limit won't exist because they are unequal. And if you wanted to, you can write this as the limit as x approaches a of f of x exists if and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. Okay, one last example. So here is f of x equals 1 over x. And I want to examine what's happening at x equals 0. So let's just say, what is f of 0? Now, if we plug that into 1 over x, then we get 1 over 0, which obviously does not exist. But then what about the limit as x approaches 0 of f of x? So first, let's look at the right-sided limit. So as we approach this curve and we go up, we get closer and closer. We keep going up and up and up to infinity. We don't stop. We just keep going. So we say the limit as x approaches 0 from the right, so a plus sign, of f of x equals infinity. Now let's look at the left side. So as we go from the left to the right and we approach x equals 0, we get closer and closer and keep going down to negative infinity. So we write the limit as x approaches 0 from the left of f of x equals negative infinity. So the left and right sided limit do exist. So then what about the general limit? Just limit as x approaches 0. Well, since these two right here are not equal, the left and the right aren't equal, then we say the limit as x approaches 0 of f of x does not exist. Okay, so we've been talking about the limit, but we keep using terms like approaching, which is not very mathematical. It's not exact. So we have something called the Epsilon-Delta definition of a limit. Now, this formal definition will probably look unreadable to you, but I will analyze each part of it. So it goes that the limit as x approaches c of f of x is equal to L if and only if for all epsilon greater than 0 there exists a delta greater than 0 such that 0 is less than the absolute value of x minus c, which is less than delta, implies that the absolute value of x, f of x minus L is less than epsilon. So the limit of f of x at x approaches c being equal to L is true if and only if this statement right here is true. So let's look more into that. So we have for all epsilon greater than 0. So choose any number and assign it to epsilon, and if it's greater than 0, there must exist some number greater than 0 called delta, such that these conditions are fulfilled. Now these conditions right here are saying that this absolute value of x minus c is basically saying the distance of the current x value we're looking at compared to the x value of the limit we're trying to evaluate it at. So the distance between that is in between 0 and delta. So basically what this means, let's say right here on our graph, we have this point c, x equals c. And right here we have a range of values. And the distance between c and the left bound of these x values is equal to delta, and so is this right bound here. Let's say we want to see if the limit as x approaches c of this graph right here is equal to L. Let's say this y value right here is L, so this point. So for all epsilon greater than 0 around L, so basically any range of y values around L, centered at L, and epsilon is our distance from the center L to the bounds on the top and bottom. Now we say we have, say, these two bounds right here. Now right here, the distance from here, from L to this upper bound is 1/2, and down here is 1/2. So in this case, epsilon equals 1/2. So we choose one epsilon that's greater than 0, and now we gotta look if there exists some distance between c right here that implies all values of their function in this range lie between L. So if we look here, let's say delta right here is equal to 1. So in this range, we have all of these points right here included, and all of these points right here included. So this is saying the x value ranging in between here will produce y values on this function around 1 and 3 right here. But since we chose an epsilon that is greater than 0 right here, not all of these y values exist in this vertical range right here. So that's saying there exists an epsilon that doesn't imply that all the values lie in that range. And since it's supposed to be all epsilon greater than 0, that implies that the limit doesn't exist because it doesn't follow this condition here. So luckily when we chose epsilon equal to 1/2, this implied right here that the limit doesn't exist. Let's say, however, we started with some greater epsilon. So let's say epsilon equals 3. And we say we're trying to see if the limit exists again at this point right here, L. So since epsilon equals 3, our range of y values is going to be 3 on this side of L and 3 units on this side of L. So we'll get something kind of like, so this whole range of values right here. Now we're inspecting the function again at this point right here, C. So let's see if we have a value of delta greater than 0 here, so a range of values of x values around C that imply all the corresponding y values on the function are within this vertical range here created by epsilon. Let's choose delta equals 1. So we'll have this x range right here. Because again, there's a distance of 1 right here between C and our left bound and C and our right bound. So let's look at all of the values here of our function that lie within this horizontal range. So we got all of these values down here, and then we have these values up here. Now, since epsilon is equal to 3, we have this vertical range. So do all of these points right here on the curve lie within this vertical range? Yes, they do. So therefore, this doesn't disprove that the limit exists. All right, so now what we would do from this point is we say, since all those values lied within our range of epsilon, then we say the limit might exist. So what we do now is we would take our epsilon and decrease it. So let's go down to epsilon equals 1. So now we have this vertical range of values right here. So now let's choose some delta around our point here, C. I'm going to choose just 1/2. So we'd have this range right here, 1/2 of a unit between C and our right and left bound. So now let's look at all of the corresponding y values on our curve that are within this horizontal range. So we get these values right here, and then these values right there. Now, if we look, does our epsilon being 1 here, does this vertical range include all of those points? No, it doesn't. It includes these points up here, but it doesn't include these points. So now that there is an epsilon that does not follow this condition, then we can say the limit doesn't exist. We just got lucky with the first guess of epsilon equals 1/2. So really our process is we just take a epsilon value and we keep choosing a smaller and smaller epsilon value until we either can't find some delta, some range here that has all y values within that range of L plus epsilon and L minus epsilon, or we keep going, and no matter how small of an epsilon we choose that's still greater than 0, we always have the values within that delta, then that means the limit does exist. That's basically what this is saying. It's pretty complicated, but it's more of a real analysis topic. It's usually included in pre-calculus and the limit definition. So, all right, so that's basically everything. I know a lot of it probably doesn't make sense, especially the epsilon delta stuff, but it took me quite a few tries to understand it myself. Thank you everyone for watching, and see you in the next video. I'll probably be doing something over derivatives and how the limit ties in with them. Thank you.